Thanks.
Thank you, Thomas, for the introduction. And yeah, this is a rare opportunity for me to talk about something other than smoke. So we'll make the most of it. You know, my PhD work was actually looking at toasting of barrels. So I worked for Treasury Wine Estates at the time. They owned the cooperage. We did a lot of work trying to understand variability in the toasting process. We're not going to talk about that today, although we are going to start a conversation about barrels and sustainability. Since the theme for today is sustainability, one of the things I really want to focus on and where I'll start. Forward. Maybe not.
Can you find the clicker?
I've got the clicker.
Is it on the power?
I've got
Look
it
at
on. But it is not forwarding. So what I want to start, we'll just start by talking about barrels while we try to figure out why this is not advanced.
Sometimes if you click inside the PowerPoint.
Seems unhappy about not having Zoom. All right, that's what we can do. All right, so we're going to start by talking about barrels because I want to set the stage for the issue or the idea of barrels and sustainability. The industry has used barrels for storing and aging wine since really before the industry. It's what we expect. It's very common practice to store our wine in barrels. But one of the issues with barrels is in order to make a barrel that doesn't leak, you have to treat the wood in a particular way. So in the picture on the right, you can see a quarter sawn log. This is taken, a picture I took of one of the cooperages we visit every year. The reason you have to quarter saw or quarter split if it's French oak is you want the grain you want quarter sawn grain because that allows you to bend the wood. And when I say quarter sawn grain, I actually have props. The end grain on a barrel stave runs, so if this is the inside face of the barrel, the end grain runs up and down. It's perpendicular to that face. And that allows the wood to be bent. If you try to do that with flat sawn wood, it doesn't bend as readily. It also helps keep the wood or keep the wine from leaking through the barrel. And we'll talk a little bit more about that and the difference between what we call cross grain or side grain, which is the face that the wine sees on the inside of the barrel, versus end grain, which is the grain at the end of the stave. And there should be bags with pieces of wood going around. So grab a piece and have a look and see if you can find end grain versus cross grain on the pieces that you're looking at. But that's going to be essential to what we're going to talk about in the next presentation. So I can pass this around. You can have a look at it. I've got pictures of it coming up. But the process of making barrels requires you to quarter saw it so that you get the right orientation of grain in the stave. The downside of quarter sawing is that it is the least efficient way to process a log into a bunch of pieces of lumber. Much easier, you get much greater production if you can flat saw it and just run the blade through and cut it into a bunch of flat slices. So it takes more wood and it takes more time and labor to convert a log into a bunch of barrel staves. And you can see in the picture on the right, there's from that log, there are probably 8 or 10 barrel stave blanks that are big enough to actually make barrel staves. A lot of that wood is going to be wasted. It's going to be used for other things. It's going to be chipped up used as mulch. So one of the key issues with sustainability in barrels is from a single mature tree, an 80 to 120-year-old oak tree, you're going to get somewhere between 1 and 3 barrels. Part of that is just quarter thawing. Part of it is if there are any knots, any defects in the wood, that's got to be called out. And so you don't get very many barrels from a single tree, 1 to 3. So it's definitely an issue in that a lot of the wood that's present in that tree gets used either as mulch or gets you'd shunt it off to some other secondary use. So you don't, one of the real advantages of barrel alternatives, this zoom thing is going to keep you from moving forward. All right, so we're going to move on and talk about barrel alternatives. These are products made usually from oak, but not in a barrel format. So there's bags of them going around. One of the first types that the industry really came to are what's known as barrel staves. They're about 3 foot long, maybe 2 inches wide, and about 1/4 of an inch or 3/8 of an inch thick, meant to essentially mimic a barrel stave, but it does have some end grain. There's end grain at both ends of the stave. When you go to make a barrel stave, you can actually flat saw this. You don't have to quarter saw it. So if you look at this as it's passed around, you can see that the end grain is not perpendicular to that flat face. It's a flat sawn piece of wood. So you will definitely get more of these staves from a log than you would barrel stave. And then the other thing about oak alternatives or barrel alternatives is they come in a huge range of different shapes and sizes. We started with this because in our limited imaginations, we thought this is great. This looks like a barrel stave. I know what to do with this. One of the things we'll talk about today is we generally don't have a good understanding of how these work compared to how barrels work. And that's what we're going to talk about today. So other reasons why barrel alternatives are more sustainable. You do get a higher percentage of each tree that gets converted into alternatives. You can pack these alternatives much more tightly and however you're shipping them. The standard 40-foot container, shipping container coming from France is only going to have a limited number of barrels, but you could pack it much fuller with staves or chips or chunks. Shipping is more efficient, yet it takes less energy, less water to produce alternatives than it does to produce barrels. And one of the biggest impacts in the whole process is actually the impact of harvesting the trees in the first place. That does a lot of damage at first. Takes a lot of energy to cut those trees down and haul the logs out. So if we can use less trees, we're going to reduce that impact as well. So there are lots of reasons why alternatives may be a good option in terms of sustainability compared to barrels. There are a number of cost reductions associated. Many of the same reasons that they're more sustainable makes them more cost effective as well. Less cost of shipping, you get more alternatives from the tree. And we all know using barrels in winery is very labor intensive. A lot of maintenance of barrels, you're filling, you're emptying, you're topping. You don't have that excess labor with alternatives. There's labor associated with putting them into the tank and with taking them out, but it doesn't require the same amount of labor as using barrels. One of the other key advantages that generally you're going to have much faster extraction times with alternatives, particularly when you get to some of these range of other shapes where you've got little beams and little sticks, you've got here cubes. So you've got all of these looking as they go around. These are much smaller pieces of wood, so we would expect that they're going to extract more quickly. And usually when people think about this being a more rapid extraction, they're talking, they think it's really based on size and surface area. But it's much, as with everything we look at, it's more complicated. So I talked briefly about end grain versus cross grain. We're going to spend a lot of time talking about that in the next 20 minutes or so, because it really makes a difference in how these things behave compared to how barrels behave. So in a barrel, the wine really only sees cross grain, the side grain. With oak alternatives, the end grain is exposed too, and so the wine can penetrate into the stave or into the piece of wood through the end grain. There have been some barriers to adoption of oak alternatives, and one of the big ones that everybody who goes to alternatives has to face is that consumers expect your wine's going to be aged in a barrel. They want to go to the tasting room and see that window that looks out on the barrel room full of shiny barrels. And there's definitely a perception that wines aged with alternatives are lower quality wines. And in some cases that's true, but it doesn't necessarily have to be that way. The other issue is early on, the alternative quality, the wood that was used for making alternatives was definitely not the same wood as they were using to make barrels. Most of the companies that are doing this commercially now are really tuned into that, and they've upped the quality of the wood that they're using. It's often the very same logs, the very same trees that they would use to make barrels. So the quality of the wood has gotten much better, and they've gotten better at managing toasting in a variety of ways. So the alternatives are definitely improving. But one of the key barriers to adoption is there really hasn't been clear guidance on how to use these products. What dose rate does it take? How long does it take? What am I supposed to do with the idea of barrels all being toasted over fires? A lot of these alternatives are convection toast. So how do I make that transition from barrel to alternatives? Most of the guidance that's out there about dose rates and time is again based on total surface area. And then there's just been how do we match this profile of the alternatives to the profiles of the barrels that I'm used to. So what we're going to talk about is trying to get past one of those barriers, the idea of how long does it take, what volume of wood do I need, how do I use these things in terms of extraction rate or extracted. So we're going to talk about cross grain. You've got the barrel stave going around. I showed that inside face. See it on this picture on the left. That inside face is all cross grain. The end grain is at the end of the stave. You can see in this picture that vertical growth ring. That's the impact of quarter sawing or quarter splitting. You can get those rings oriented vertically and perpendicular to the stave face. And that's what allows us to be able to bend that stave into the face of the barrel. One of the key things, again, with barrel staves is yes, every barrel stave has end grain on it, but it's outside the barrel. So the arrow there points to the barrel crows. That's where the head of the barrel sits. So the wine inside that barrel doesn't ever see end grain. It only sees cross grain because the end grain on the barrel stave is literally outside. It's outside the barrel. The wine's on this side of the crows. The end grain's on the other side. So it never sees end grain. So why does that matter? I mean, we've known for a while there's a difference between extraction rate for end grain versus cross grain. There, in fact, were some people making alternatives that did some cross cutting to enhance the amount of end grain. So it's been around this idea that end grain is different than cross grain. We've done some electron microscopy. So Mackenzie, over in the far corner here, is the graduate student working on this project. We've spent a lot of time up in Pullman taking pictures of oak at very high magnification. And this is a picture of end grain taken with an electron microscope. And the pore sizes, the pores you see here are actually the xylem vessels in that piece of wood. And the reason we see growth rings in oak is you have a layer of what they call spring wood, which is the larger xylem vessels. And then after that part of the growing season, the tree will lay down some what they call late wood that has much tighter pores. And so you see this alternating pattern of large vessels and smaller vessels, and that's what we see visually as the end grain. But the key thing about the size of these pores is they're large pores. They allow the wine or whiskey, if you're doing scotch or something like that, it allows direct access into the center of the piece of wood. And these xylem vessels run the whole length of that barrel stave. So there are places where they're blocked, but it does allow for much more rapid entrance of the solvent into the center of the stave. When you contrast that to the cross grain, so this is a picture taken of the inside face of a barrel, the pores are much smaller. They're, instead of one pore being 300 microns in diameter, in 50 microns, we've got 5 or 6 smaller pores. Wine can still penetrate into the wood from the cross grain, but it's a much slower process than coming in from the end. And so when you start to look at oak alternatives, where we've got a whole range of essentially relative amount of cross grain to end grain. So if you, who's got one of the long barrel staves? Those come back here. So you look at that, that's 36 inches long, 2 inches wide, 1/4 inch thick. There's only a tiny amount of end grain at the end of each stave. But if you contrast that to something like this, shorter piece, and we've got much more end grain compared to cross grain for that piece. This is a much more end grain. And when you start to get the smaller pieces, the cubes, you can get to the point where end grain can be half of the total surface area. And so that has a huge impact on how that piece of wood or those pieces of wood are going to extract. And so we set out an experiment to try and understand that. And this is the basis for it. So we started with a piece like this, 25 centimeters, 10 inches long. And that has a total surface area of 318 square centimeters. And of that, about 3% is end grain. The rest of it is cross grain. If we then take another piece like this and cut it in half, what have we done? We've introduced 2 new end grain faces, right? Total surface area only goes up by the amount of the 2 end grains. So we go from 318 to 325. But we've doubled the amount of end grain. So the end grain to cross grain ratio is now 6% if you cut this in half. You cut it in half again, you do the same thing. The surface area goes up a little bit because you've exposed some more end grain surfaces. And now we're at 340 some centimeters squared, but it's 12% end grain. And so on and so forth. And you get to the last pieces, which are, one like this. So it's about 2 centimeters wide. And the end grain to cross grain ratio is about 50-50. There's almost as much end grain here as there is cross grain. And so what we've done is set up a circumstance where with each cut, we've doubled the amount of end grain. And we're just going to look at what impact that has on extraction rate and try to understand how the ratio of the two affects how quickly things are going to be extracted. And so we did that. We set it up in a bunch of 4-liter, what are we calling them, Mackenzie? Just water bottles, kind of like growlers, stainless steel. 21 grams of oak. One of these pieces is about 21 grams. We put the same, so we put this amount of wood, whether it's 1 piece or 16, into each keg. We did it in triplicate, 120 days of extraction. Mackenzie collected samples on day 2, 4, 6, 8, 10, 15, day 30, 60, 90, 120. So she was very busy, especially in the beginning part of this. These were all medium toast, convection toasted material. And then every time she took an extract, she ran out of the GCMS to look at a range of about, I think there were 7 or 8 aroma compounds that we measured as part of the study.
French or American oak?
French.
This is French. We're looking at both in some follow-up studies, but so the key is with this design, if the increase in extraction rate is only due to surface area, the surface area from the shortest piece, from the single piece to the multiple pieces, only goes up by about 45%. So about 50% more surface area. So if it's only due to increase in surface area, we should see increase of about 50% from the longest piece to the short. The end grain to cross grain ratio goes up by 1,600%. It's 16 times higher than the starting piece. What we found when we looked at the extraction curves is that it comes out somewhere in between. So it goes up both with surface area, but more importantly with end grain to cross grain ratios. The more end grain you have, the faster the extraction. So from the curves, from the raw extraction curves, Mackenzie worked with Dr. Coleman here, the second row back, so we developed some predictive models that we can look at individual compounds. We can look at all the different compounds we looked at by the end grain to cross grain ratio. So in this curve, the orange line lowest curve, that's for the longer pieces. That's where you only have 3% of end grain. And the fastest curve, the one that goes up most quickly, is from the shortest piece. This predictive model gives us two things. One is it gives us a theoretical maximum extraction. So this is what we're going to get from this piece of wood if we extract everything. Which is cool, because that tells us for any piece of wood what we can expect to get from it. And it also gives us an initial extraction. How quickly does it extract based on the end grain cross grain ratio? And so we can do cool things like figure out if we want to know how long is it going to take us to extract 50% of what's there. We now have a theoretical maximum. We can figure out what it's going to take, how long it's going to take to get to 50%. And so with the longest piece, it takes 48 days to get half of the furfural out. So it's specifically for furfural in this example. But it takes 6 days in the shortest piece. So we're 8 times faster by going to smaller pieces. We can do the same thing at 75%, 95%, whatever you want. You could also say, for example, I have 90 days to get for this wine to be on oak. What percentage of the furfural I'm going to extract in 90 days? So we just go to the bottom line, which is time in days, go to 90, draw vertical, and see where it intersects. See what percentage will you have extracted if you have 90 days for this wine to be on oak. And we can do this examples for furfural, we can do this for other compounds as well. One of the nice things is, because we now have a theoretical maximum, we can normalize this and put all the different oak compounds on a single plot. So we can look at furfural, which it turns out in this case was the fastest to extract. We can also look at cis and trans oak lactone, look at glycol. And even though I'm not talking about smoke, I'm still talking about glycol. So this spot in particular is for the shortest piece. You could do the same thing with other pieces and see how different compounds are extracted. I think it's important to understand that all of these oak compounds do not extract at the same rate. Some of them come out more quickly. And I think you understand that intuitively, but it's nice to actually have the data that shows that they are different and by how much. So this is in that piece that looks like this. We also had previously done some work looking at extraction rates in a cube like this. So roughly 1 by 1 by 1. And you can see the extraction rates don't exactly look the same. So here's in the stick, which is about half end grain. This one, the cube is about 2/3 cross grain, 1/3 end grain. And the extraction rates are slower. But notice the order is the same. You still have furfural coming out first. Cis and trans oak lactone are coming out more slowly, as does 5-methyl furfural. So we can look at this and see what the impact of different shapes is on these extractions. We can also extend this model to look at other things. So in this particular one, example, we're showing the cube, right? So the cube versus segments, which are the kind of square piece that comes from, yeah, there's a segment. Yeah, something like this, right? So a cube, a segment. We have the staves, which are the ones, the long pieces in the back. And then there's also a comparison to barrels and puncheon. So this model allows you to put in how much surface area there is total, how much of it is cross grain, how much of it is end grain, and then it'll develop what the curve would look like, what the extraction curve would look like. So we can compare how different formats are going to behave for individual compounds, for any of the compounds we're interested in. And again, we can do the same sort of thing. So looking across these 5 or 6 different formats, and we have 90 days to use them. The cube, this piece, we extract about 95% of the furfural in the 90 days. With the segment, it's about 80%. The long stave, we're down to 40% of the total furfural extracted. You can see a barrel is 25%, puncheon, so the larger format barrel is less than 20%. So you can get a comparison of how quickly different formats are going to extract. using something like this line. And again, we can look at how long does it take to extract 50% of this thing, 10%, whatever your target is. You can see to get to 50% of the furfural, the cube takes about 20 days. Puncheon takes 285 days, almost a year to get to the same point. And intuitively, again, we kind of understand that, but it's nice to see it laid out here. One of the key things about the model as it's developed right now is this was based on the first set of extractions, which were all done with medium toast. We've done some other work, and when I say we, I mean Kenzie has done some other work looking at different toast levels. And so you see different amounts of maximum amount of furfural based on the toast level. It peaks out in medium. It's lower at lower toast levels, it's lower at higher toast levels, it reaches maximum. Glycol behaves differently. It keeps going up. Most glycol, the highest concentration is going to be in the most heavy toasted wood. And so we know the next layer of this model is to look at different toast levels. Those extractions have been started. How many days are we in? 30?
Over 45.
45. Okay, almost halfway there. All right, so that's the next step, is to take it to a third dimension, which is to look not just at size and shape, but also at toast. And so just to wrap it up, what I've looked at, or what we've talked about today, is really trying to understand oak extraction kinetics using by modeling how the two different grain types interact to produce an overall extraction rate, and also how much material gets extracted, what's the maximum amount you're going to get from this particular piece of wood. Again, the current model that I've been showing you is based on medium toast. We're in the works to look at light, medium, heavy. We're also going to look at whether you stir it or not stir it. So that's the other bit of it that is still in the works. But one of the key things is this model can be used in a variety of ways based on what your interests are. If you have a limited amount of time and you want to know how much you're going to get, we can do that. If you want to know how long it's going to take to get half, most of a particular compound, we can figure that out. And it'll tell you that it work towards getting optimal sizes depending on what you're trying to do. But we're still very much a work in progress, but I think this is really going to go a long ways towards that barrier to adoption of not really understanding how to use these kinds of alternatives. And with that, I don't know that I have time for questions, but I wanted to thank Scott Labs for support for this project and point out that all the microscopy images were taken at the Franceschi Center in Pullman, which supports electron microscopy across all of us. Thank you.
Thank you, Tom. I think we, in the interest of the program, which is very long, very full, we'll take our break as scheduled now. Tom will be here all day.
Yep.
So please ask him some more questions. Thank you, Tom.
So ready to set up its back. Daryl's ready to talk a lot about. Great. I mean,
No.
Yep.